Hello, we are Yanni Spiritus and Rui Pinto, and our project is called the Maze Runner. So our vehicle is meant to follow the paths and avoid the obstacles within an environment that is meant to represent environments that are generally too small or dangerous to be navigated by manned vehicles in pursuit of a certain object that's represented by our goal state. But before we could do the maze solving algorithm and build up that logic, we first had to create, basic motor functionality. We had to distinguish between the maze path and the floor and the goal state, and also sense those obstacles before being able to avoid them.
So here's a picture of our mechatronic system. On the front, there's an IR distance sensor which detects obstacles in the vehicle's path. On the bottom, facing the ground, is an RGB color sensor which is used to keep the vehicle on the path, as well as a signal when the device has reached a junction or the goal state. The system is equipped with a caster wheel, allowing the vehicle to turn freely. The vehicle is driven by two independently controlled stepper motors, which directly drive the two drive wheels, and tucked behind the wheel is a Hall effect rotary encoder used for feedback control. Here you see a top-down view of the system. The MSP is powered by a 9-volt battery whose output is converted to 5 volts using a simple voltage divider. The MSP is responsible for all sensor processing and control output. The system is also equipped with an Arduino Due, which is used simply to collect data from the RGB sensor via I2C communication and then relays that information via UART serial to the MSP. The Arduino is powered directly by a 9-volt battery. The MSP feeds control inputs into two stepper motor drivers, which drive the stepper motors. The motor drivers are powered separately by a 5-volt 2-amp battery pack. Here's a flowchart showing how the software of the system works at a high level. Color data is received via serial from the Arduino and classified based on experimentally determined thresholds, and a global color variable is updated accordingly. The system pulls the color variable every loop and determines its next action based on the current color. If the color is not one of the specified values, the system swivels until it observes either black or blue. If the color is green, the goal state has been reached and the system will loop infinitely. If the color is blue, the vehicle has reached a junction. The system will check if the junction has been visited previously by comparing its current position to the position of all the previously visited junctions. If it has never been visited, the vehicle will explore the area around the junction to see what paths exist. It will then calculate the straight line distance to the goal position from each available path. It will then choose the shortest unvisited path or go back the way it came from. If the junction had already been visited, the system would skip to choosing the shortest path immediately without having to re-explore what paths exist. After making the necessary turns, the system pulls the color data once again. If the color is black, the system first corrects its relative position using the PID control signal and then drives forward another step, updating its X and Y set points along the way. The PID control is updated at 10 Hz and is calculated by comparing the set point X and Y position and the position calculated by the rotary encoders. The rotary encoders update using an interrupt which is triggered when their output goes from low to high. Here is a clip of the system making a decision at a junction. It detects the blue tape, signaling that it needs to make a decision. It first moves past the junction to see if a path exists in front of it. It then turns 90 degrees to the left to check for a path, swiveling in small angles to check the entire area. It then turns 180 degrees and does the same thing on the right side. It then calculates the shortest straight line distance to the goal state and turns that direction. So here it chose to turn left. Here's a clip of the system solving a full maze. This maze is an easier maze because it does not have to backtrack at any point. So you'll see here it's going to explore the junction as we talked about in the last clip, and then it's going to make a decision to turn left, explore this junction, and again it won't have to backtrack because the shortest distance is obviously going to be to the right. So now it has to go to the final junction, and it's obviously going to choose to turn right because there's no other option. And then it needs to correct its path a little bit here, and it's finished. So here's a clip of actually a harder maze to solve, which forces the system to backtrack. So as you see here, it makes a decision to turn left because it appears the goal state is somewhere to the left, but actually the right choice would be gone to straight. So it's going to realize it hit a dead end, and then it's going to see that it's back at the same junction it visited and not explore. It just took a straight left turn, and then here again it's going to have to explore, and it's obviously going to choose left, and then again its only choice is to turn left here. So it eventually will reach the goal state. But in this case, we had to backtrack and realize that we were at the same junction.
Now, despite our overall success in reaching the goal states, there's still significant room for improvement. First, the system would sometimes mistake blue tape for black tape, or not recognize the blue tape at all. And the best way to improve this detection consistency would be to use a higher contrast color of tape, like red for example, unless a higher resolution sensor is available. In addition, The system could become more robust to a wider range of complex environments by employing, for example, a camera to navigate a 3D environment. Finally, a trade off we had to negotiate during testing was the sacrifice of speed for accuracy, and overall higher signal fidelity would lend itself to the system maintaining its high rate of accuracy while increasing speed. Thank you for your time. Are there any questions?